Welcome back. This video we want to take a look at the relationship that exists, or I should say a relationship that exists fundamentally between potential and kinetic energy. So let's just go ahead and jump in. So energy is energy. It's just that we tend to talk about it in different ways. So there's potential energy, there's kinetic energy, and there's mechanical energy. You can think of electrical energy from sunlight. There's various ways of referring to energy, but all energy is the same. The only difference is it's transformed and transferred from one system to another. And all that means is for instance, like if this object is just sitting here, it's not doing anything, it's just sitting there. And then all of a sudden it's in motion. We would say that some work is being done because it's being forced a certain distance. And we know that force is mass times acceleration. So the fact that we're talking about acceleration implies that there is a change in velocity per change in time. So all of this is in here, and this is in here, so it's right there as well. So when work is occurring, the acceleration of mass is occurring over a certain distance. Well, when that happens, that work, it translates into a certain amount of energy, and energy is a capital E. Okay, so what we want to do is take a look at where does this potential come from and what happens to the potential for something to actually move, which means some work has been done or is being done. Okay, so let's just go ahead and let's back this up, and let's now put this into something perspective that's a little more organized as far as potential and kinetic energies go. So when potential energy, you will typically see it written. All right, potential energy we know is the stored energy. All right, and you typically will see that written as GPE, which means gravitational potential energy. All right, and that is the mass times acceleration due to gravity times height. And how we get that is like this. Okay, so you've got an object. That object is down here, and then all of a sudden this object is raised up to a particular height. We don't know what height, it's just some height. We look at this and we realize that right here, this change in y equals some sort of height. All right, and this height is now greater than 0. So here we were at ground. All right, and ground equals 0. Okay, and so up here, this is where y is greater than 0. Here, y equals 0, right? So this height right here, there has to be a change in height. Because the object is above the ground, then the acceleration due to gravity is trying to pull the mass of this object downward. And so you can see that there's mass being accelerated downward due to some height. All that is a result of gravity. And so there is potential for the object to do some work. Okay? So fundamentally, the way energy is stored, one way that energy is stored in objects is for those objects to be raised a particular height from ground zero. Okay, that's gravitational potential energy. Okay, the opposite of that would be the kinetic energy. All right, and kinetic energy, you'll see it written like this, and kinetic energy is 1/2 mv squared. Now there will be another video where I show you how we get 1/2 and how we get squared velocity and all that other good stuff. But let's just think about the concept of kinetic energy. We know that kinetic energy, all right, that is the energy of motion. Okay, it's the energy of motion. All right, well, the object has mass, check. Okay, so if it's the energy of motion, it makes sense that velocity is there because there is some motion. So now let's go back to this here. Let's think about the unit here for a second. We've got mass. Mass we know is kilograms. All right. The acceleration due to gravity is meters per second squared. That's what the acceleration due to gravity is. Well, we know that all of this is a Newton because kilogram meters per second squared. So now what that means is we have to multiply times height, which is measured in meters. So if we bring this down, we have a Newton meter, and which is a joule, okay? Capital J. So if you think about this, what we have is kilogram meters squared per second squared. If you look at all of this right here, you know, this meters times this meters would be meters squared, right? So now let's think about this here for a second. This is kinetic energy. So when we're done, we have to have the same unit. So if you're not sure why this has to be squared, the first thing we can do is just go back to the basic concept of kinetic energy. Mass is kilograms. Velocity is meters per second. So now we look at this and we realize it's not the same as this. Okay, how can we get that to be true? Well, this right here, just this part right here, that's meters squared per second squared. So now we should be able to draw. We should be able to see, draws to that conclusion that, wait a minute, if that were squared, then that means this would be squared. So that'd be kilogram meters squared per second squared, which would be the same as a joule, which is the same as a Newton meter, right? It's the same as a Newton meter, right? So the unit of energy, Newton meter, but we more specifically use a joule, all right? So we can see that they're both interrelated, all right? Just from understanding the concept of potential, something is there, motion, we've got velocity, and since we're talking about matter, then mass has always got to be a part of what we're doing, right? So now that we understand those fundamentals, let's take a look at another basic here that is quite important. All right, quite important. So your studies in chemistry and physics, you have talked about. You have talked about the law of conservation. Okay. So you know, chemistry, you talk about the law of conservation of mass, you know, the law of conservation of energy, law of conservation, so of matter, you know, etc. Whatever you start with is what you end up with. In physics, we can talk about like the law of conservation of momentum. All this is the law of conservation means that no matter what you're talking about, the conservation part means whatever you start with is what you wind up with, because it is in a system, all the parts are there. They're not destroyed. So whatever you start with is what you end up with. So with that said, let's just think about this for a moment. All right. Let's think about this for a second. I'll just stick with this blue color. Okay. So you have energy and you have a total amount. Well, what does that equal? So let's think about this. Whatever we start with is the potential energy plus whatever energy there is from the motion. So, and and whatever other energy is there. But as a rule of thumb, we talk about it first from the perspective of potential and kinetic energy, and all that is there, right? So now let's go back to the example we had earlier. Okay, go ahead and get a shape out here for us. So remember this, right? Remember we raised this up, right? And when we did, so up here there is some potential energy. Down here there is some potential energy. Up here there is some kinetic energy, and down here there is some kinetic energy, or there's a possibility that there is. So let's think about this. All right. So the energy total, we can just say, so the total amount of energy, let me go back, put everything in the same color. Just, I know some people like those, the consistency, right? So we've got the total amount of energy is, if you think about it, the energy at the top plus the energy at the bottom. Okay? So now, if that's true, then what that means is the energy at the top equals the energy at the bottom. It has to, because let's think about this. Down here, if this object is not moving, then, or down here at ground zero, if this object right here is down here at ground zero, then we would say its kinetic energy is 0. Up here at the top, we would say that the potential energy here is greater than 0. As this thing falls, by the time it hits the bottom, then it's got some motion. All right, it's got some motion. All right, so now let's think about this for a second. Energy, we know that the total amount of energy is this. So that means there's potential energy at the top, right? And then there is potential energy and kinetic energy as well at the bottom. Okay. And I could put bottom here and here, or top here and here. I could put bottom here and here. It's the same thing. I'm just putting it all in parentheses because we know it just would bring it all together. All right. So now let's think about this just a little bit more. All right. We know that potential energy, right? We know that potential energy is mass times acceleration due to gravity plus height. Plus, we know that kinetic energy is 1/2 mv squared, right? And all this is up at the top. Then potential energy again is mass times acceleration due to gravity plus the kinetic energy, which is 1/2 the mass times velocity squared. And this is at the bottom. So now let's think about this for a second. Let's think about what's happening at the top. At the top, we would say that all of the potential is there, but as soon as you raise this thing up and you stop, we would say that it's not moving. So we would say this equals 0 up at the top. Conversely, when the object falls down and then hits ground zero, at the bottom, it no longer has potential, so we would say this part is gone. It's 0. So it's at 0 height. If height is 0, then that expression is 0. At the top, if there's no velocity, then that entire expression is 0. Right? So what we wind up with is this at the top equals 1/2 mv squared. And of course, this is at the bottom. And so we see again that we have this expression is true. All of this brings us right back to that. This makes sense. Our potential energy up at the top, right, equals our kinetic energy at the bottom. They match up. They have to. Okay? So keep that in mind. All right? And then with that said, right? With that said, let's think about this from one more perspective. Let me go with a slightly different color. If we are at this point here, this is the halfway mark. This is the halfway mark, all right? So if we're at the halfway mark, then we have 1/2 of the potential, right? We have 1/2 of the potential that is there, but at the same time, this half of the kinetic energy has occurred. So at the halfway mark, we would say that the potential energy equals the kinetic energy and vice versa. They are equal to each other. All right? It's just a basic concept. You've got to keep that in mind. This will help you solve these problems that you're going to work on. These problem sets that I give you, this is going to help you do that. If you can understand these concepts here, then it's just a matter of plug and chug for the most part. All right? I hope this kind of helps put a little bit in perspective law of conservation of energy, and we can get a little more complex in this. This is just the basics to get us understanding the relationships that exist between the potential versus the kinetic energy that you have in a system. And again, remember, a system is all the parts that are there, all the mass that we're looking at that can go in motion or is in motion, and how they're all interrelated, because they are interrelated. All right? Hope that helped. I will see you in another lesson real soon, and stay curious. Good talking with you again. Welcome, and I'll see you later. Have fun.